Well, welcome back for the third installment. And so we were slowly moving down towards the dark energy, but we were just here. So here are different ideas what it could be if it isn't a cosmological constant. Well, what could be behind? So it could be a cosmological constant. And then maybe we need the anthropic principle, or the data could be wrong. Well, probably not. Or it could be that we make some mistake with fundamental assumptions. So just to remind ourselves that we nearly always work within the model context. And so, of course, if the model is wrong, then the answers will be wrong. And so one of the basic assumptions is the Copernican principle. Let me switch to here. And if the Copernican principle is wrong, then our conclusions about the need for dark energy can be wrong. And the typical model would be a void model, where we are in the center of a huge void. Of course, then you need to explain where the void comes from. And you have problems with some observations, because then typically galaxies should fall away out of the void with high velocities that we don't see. Now, another possibility that is kind of subtle and cute is the fact that GR is a nonlinear theory, and so we have to be a bit careful about what that implies. So I should probably go through this quickly, but since I have worked on it and I really like it, I'm going to spend a few minutes on it. So the idea is the following, that what we have been, so the universe, as we know it, is not perfectly isotropic and homogeneous. Otherwise we wouldn't be here. Okay, so there are fluctuations. And so what we did, we said, well, on average, it is homogeneous and isotropic. And so we work with the exactly homogeneous and isotropic Friedman, Lemaitre, Robertson, Walker metric that is an exact solution of GR, and we use the evolution of that exact solution, and then we use this as our average universe here, for example, for the supernova data. But that's not what we should do. What we should do is we should actually evolve the perturbed universe and then average afterwards. And because GR is nonlinear, averaging and evolution don't commute. So it makes a difference if you average and then look at the exact evolution of the averaged solution, or if you evolve your perturbed universe and then you average. You don't get the same answer. That, everybody agrees on that. What people don't agree on is whether it's important or not. And so there was some work quite some time ago where people try to calculate this, and so you need to, then everything becomes quite complicated, but you have to average over some domain, and then you can get a set of effective equations in full generality, and these equations, they look exactly like the Friedman equation here. This should be a square. Oh, I think I have never noticed that before. Okay, that should be a dot over a square, and then this is the rho. And then there is an extra term, okay? And also the acceleration equation has an extra term. And so depending, so you see the acceleration equation normally has this part, and so this will slow down the expansion of the universe, but there is an extra contribution that comes from the inhomogeneity. So this is present in GR. And so depending on the size and the sign of this term, the inhomogeneities could be apparently accelerating the expansion. Okay. And so that's quite exciting. It's also exciting because this term probably becomes important when structures become nonlinear, and that happens recently, and so that would fit perfectly with the coincidence problem. That would naturally explain why dark energy is becoming important now. And the amazing thing is, so usually I talk about crazy things like modified gravity theories and dark energy, and no one ever complains that these are totally crazy. But when I gave the first time a talk about this, people were jumping up and shouting at me, "This is crazy! I know it's wrong, I can't prove it, but I know it's wrong." So that was like a very eminent scientist. I mean, I agree, but it really surprised me. So this has really the tendency of getting people very, very excited. Okay, so we decided to look into this with numerical methods because analytically it's very hard. You can't do perturbation theory because perturbation theory diverges, so you just don't know what the answer should be. You can also show that with Newtonian simulations, the effect is exactly zero because in Newtonian gravity it is a boundary term, and if you work with periodic boundary conditions, you don't have a boundary, and so by construction it's zero, and so you really need to work in GR. And so that was one of the motivations to write the relativistic n-body code, where a line element is not actually that, but because you have to add vector and tensor parts. But this is just to show, okay, how would then such a correction show up? And it would be in what we usually call the zero mode, in the sense the k equals zero contribution to these potentials, which are the average contributions. And if you have a non-zero average, normally you assume that the average is zero, but in this case you generate dynamically a non-zero average in the evolution, and so then then you can think of, if you get the non-zero contribution here, you can think of as a redefinition of time, but if you get the non-zero contribution here, then it gives you a redefinition or a correction to your expansion rate. And so what we are looking for is a non-zero contribution between these two effectively. And so here you see an example how the universe looks like, and as it evolves. So in this plot, in principle, there is also density. Density goes, and of course there is also redshift, and I should really know. So this is high redshift, this is not so high redshift, and this is low redshift. So here density perturbations are small, the potentials are small, 10 to the minus 5, and they are the same. And then as the universe evolves, the density goes crazy because you form a nonlinear structure, but you can see that the potentials stay beautifully small. And but you start to generate a difference. But this difference is very small. You see here it's 10 to the minus 5, and here it's magnified by a factor of 100, so this is 10 to the minus 7. And if you are more careful, and you look at the correction to the Hubble rate, okay, so you find that it's really tiny, 10 to the minus 7, and it slows down the expansion rate of the universe. Okay, and then if you write that in a paper, then the people who liked, so this a priori looks like it kills back reaction, this scenario, but then the people who like the scenario come and say, but this is in a specific choice of coordinate system. And in another choice of coordinate system or gauge, the result is totally different. And this is actually true. And in addition, there is an additional constraint from the simulations themselves. So it's not really sure whether this really kills the whole scenario. So to be sure, we have to look at observables, and again, that's a very generic statement in GR. Only observables are well defined, and anything else that you calculate, you can get wildly different answers depending on how you calculate it. For observables, you have to always get the same answer because you can go and observe it, and there is a unique answer. Okay, so we also did that. That is now quite recent. And so we run a huge simulation with our code. This is one of the biggest, I think, that was ever run. It's 7680 cubed grid and as many particle, and we saved the light cone. And then we did ray tracing using what's called the Sachs equation that also allowed to calculate distances. And so here is a distance redshift diagram where we divided by the background distance that we used. Okay, and so you can see that you don't really get the deviation, but you get a big scatter. Normally we think of this as lensing. So this we would normally say this is lensing scatter. And the average of this is actually much, much closer to what you expect. But you also see that depending what you average, you get slightly different answers. That's another cute aspect. So if you can, for example, see that the distance modulus is more biased than 1 over the luminosity distance squared. This was actually predicted using perturbation theory. But you can also see that your PDF is skewed because light rays tend to go through underdense regions more than overdense regions, and so most light rays they are demagnified, I think, so they are on this side, but there are strongly magnified events from overdense regions, and so but the average is actually basically the same. Okay, so then you can ask the question, well, is there an effect? And you analyze the fake data set that is extremely good, better than what LSSD will ever get. So if this doesn't show an effect, you don't have to worry about it, basically. And so you can see we do see an effect, and so here you get the posterior the contours depending on what you average, but they're all biased by a tiny amount. Okay? This was the input model for this run. And but the main bias here comes from the shape of the PDF, and if you bin it so that it becomes Gaussianized and you use 1 over dl squared, then you really go exactly around the input model. And so that's consistent with back reaction being completely negligible. And so there are some tiny loopholes still, but for me at least, back reaction exists, but it's very small, I think. I'm quite convinced. Which is a shame. I actually like the back reaction scenario because we could have forgotten about all the dark energy problems, except we would still have to get the cosmological constant to 0, and it would have explained coincidence. Okay, so this seems not to work. And so now, finally, we are really reaching the point where the only answer, if we don't like this, and we think the data is not wrong, and we think that these don't work, then we should be looking at dark energy. But in any case, sorry, fairly unreadable from the back, in any case, even if we think it is a cosmological constant, we want to test whether it is a cosmological constant, and to test that, you need to have some framework that goes beyond the cosmological constant, so you can actually test it, right? So in any case, we want to do it. And the short comment I wanted to do that already came up yesterday is that we actually have seen already an accelerated expansion that is not dark energy. And here is a little calculation using inflation, but basically calculating what is the equation of state during inflation. And it is given by this slow roll parameter epsilon. So if epsilon is non-zero, then the equation of state is not -1. Now, the epsilon parameter also tells you how many gravitational waves there are. And how many primordial gravitational waves have we seen? None. Okay, so we cannot actually say that W is different from -1. However, the evolution of W is linked to the first and second slow roll parameter, and they are also linked with the deviation from a scale invariant spectrum. And we have seen that the spectrum is not scale invariant, because basically, if it was a cosmological constant, we would be in exact de Sitter, there would be no extra scale dependence, so you cannot generate a deviation from scale dependence. So this really shows the fact that NS is not 1 tells you immediately that we are not in an exact de Sitter, and so we are not seeing an exact cosmological constant. So basically, either W is not -1 and it's just too small to be seen, or it's not constant. And so this is a fairly direct observational evidence of dynamics in a phase that looks like it's due to accelerated expansion. And if it happens once, maybe it can happen twice. It's of course no guarantee. Okay, so how can we then model dark energy? So the first thing you would try is to try to write down specific models, and that's what we are going to look at a bit first. And typically you use the action formalism that I will remind you of, but then this is a bit problematic because there are many, many different models. Maybe firstly you probably don't want to check 100 different cases every time you get a new data set. You may have forgotten some. And so then it is much better to have some kind of framework that group together many, many theories. And so at the action level, that's what we use at the moment are effective field theory approaches. And then you can link them, or you can go closer to a more geometric description by using fluids or what we call phenomenological parameters that I will introduce at the end. And then tomorrow, then the goal is to go to down here and see, okay, what are actually our constraints on these parameters. Okay, so here is the slide that you already saw. If we have an action, here is the action is a case of a canonical scalar field that is minimally coupled, so it's just the sum. And then you can calculate the equation of motion, the Einstein equations, and so the variation of this gives you the stress energy tensor, and the field equation just using a variational principle. And you have to be, however, a bit careful, and I will go back to some of these things. So even if you calculate this, there are things that may not be so obvious. For example, your model could be unstable. If you calculate your speed of sound squared might be negative, and as we discussed, that would actually be a problem for your model. And of course, we need to also give the action. Okay, and so now, here is some practical, for all those who have forgotten how to calculate variations, so you can do it with the Euler-Lagrange equation, where I wrote here a simple example. So that's for a degree of freedom that depends on some generic variable x, okay? And here is our Lagrangian, here just the field part. And okay, and so we have to vary that one, and so let's actually quickly do it. Maybe we can, for a change, do it all together, but I'm very stupid, and so you have to explain to me what to do. And so maybe, okay, here is the metric, and so the first question is, what is this object? So this is square root of minus determinant of the metric. And what is square root of minus determinant of the metric? I'm sure each word on its own makes sense, it's just a combination. So my metric okay, I can write it as a matrix. Now that's what this ds square equal minus dt square plus a square dx square means. So what is the determinant? Yeah, exactly. And so the determinant is minus a to the power 6 is just the product of the diagonal elements. And so the square root of minus determinant g therefore is a cubed. Okay. And now f, if I want the field equation for my field phi, I have to replace f by phi. And so what is dl by d phi? What is G00? Maybe I should also say. What is G00? It's minus 1, because it's the inverse matrix, but it's diagonal, so it's minus 1, 1 over a square, 1 over a square, 1 over a square. So this is 1. Actually, the G00 I only wrote if you want to calculate this. Otherwise, I could just have written minus 1/2. Okay, so what is dl by d phi? dv by d phi, yeah? So let me write this as v prime of phi but then we shouldn't forget these factors, so we have the a cubed in front, and then we have dl by d phi df prime, but what is the x here? What is the variable on which phi depends if it is exactly isotropic and homogeneous universe? T. So x is t, and so f prime is phi dot. And so what is dl by d phi dot? Yeah. Minus a cubed phi dot, okay? And now the hardest part is now getting that you have to take the time derivative of this. And so we have d by dt of dl by d phi dot, and this is h. Let me write a dot over a cubed phi dot. Yeah, so that's when we take the derivative of the a, but the phi also depends, so we get another term that is just minus a cubed phi double dot. And so the Euler-Lagrange equation then gives, so I can now take the a cube outside. And so we have, so it's the minus step, so it's a phi double dot plus 3a dot over a phi dot plus v prime equal 0. Okay? And so this is the equation of motion that you cannot read from the back. I know you should sit in front. Okay, but you can see this is not a very hard calculation.
So the square root of minus g is not supposed to be an imaginary number?
No, because so this is the determinant, right? And so the square root, and so because we have a Lorentzian metric, so with a minus sign here, or I mean we have an odd number of minus signs, and so the determinant is negative, and so minus the determinant is positive, and so here you can see it explicitly that the determinant is minus a to the 6. Okay, and so this was not so hard. And so here I don't have the R. To do the variation of the R, you should look at the book about GR. It's not extremely hard. But you have to be a bit more careful because you need to know what this derivative is. And then you have to be, so then you have to, you can show that you get effectively this result. But that's left as an exercise for the audience. Okay, but now you know, in principle, at least you have a little reminder what you do. Okay, of course you should also do it for the perturbations and so on. So but then typically you do it with Mathematica. Okay, but it's in principle there's no magic involved. Okay, so once I give you an action, you can basically crank the handle and the equations drop out. Practice takes a while, but okay. So what? Then the question is, okay, what are typical actions? And so the action that we have looked so many times already is the action of the canonical minimally coupled scalar field. And this is, in the dark energy context, this is called quintessence typically. And it was invented in '88. And I will probably normally not have a very detailed reference list. Okay, so this you can generalize. So this part here is called the kinetic term, and you can generalize this by just putting in a function of the kinetic term, and then it's called k-essence. So this looks very funny, but it's the generalization of this, and it's still minimally coupled. And so both of these we would call dark energy in the sense that they're an additional fluid rather than something that modifies gravity. But you can do other things. right? Normally the Einstein-Hilbert action, so the action of GR is just R, or constant times R. And so you can, instead of using R, you can use a function of R. Okay. And this is called f of R. And that probably goes back to very early times, shortly after Einstein and Hilbert proposed R as the action of GR. People thought, okay, what if we have a function of it? Then another class that's also very old are so-called scalar tensor theories. So the scalar part is the scalar field, the tensor part is GR, because the propagating degrees of freedom of GR are tensor waves, and scalar tensor because there is a direct coupling, right? So far we always had R plus an action of phi, but here there is a direct coupling phi R. And so this really now modifies gravity in a direct sense. It gives you a fifth force. And but then you can show that this class of theory and that class of theory, okay, with a different shape here, they're actually the same, because you can do transformations between these two theories. Basically, the df by dr becomes your scalar field. Okay, that's something that you need to show, but I don't really have the time. So if you want, we can look at it offline or in some review. And then you can so this is scalar tensor. Well, if there are scalars and tensors, there could be vectors, and so you can look at scalar vector tensor theories. I mean, this is a bit the history of, okay, what can you possibly come up with, and whatever you can possibly come up with, people have pretty much come up. And so the tensor vector scalar theory, for example, is actually an implementation of the Mond idea for dark matter. And so generically, vector fields are appear not to be so good for accelerating the universe. And but nonetheless, they're interesting, and you can do stuff. And then, of course, you can ask yourself, so what is the most general theory that you can write down? And actually, people worked in the like 10 years ago or so, people laboriously worked towards the most general theory, and then there were several groups who at the same time more or less invented the most general theory. I'll get back to the small print on that in a moment. And then someone said, okay, we were the first. And then another group said, like, okay, let me check. Oh no, there was someone in 74 who did it. And so that's why these are now called Horndeski theories, because Horndeski, for his PhD thesis in 74, he looked at the most general scalar field theory and the most general vector field theory, and then he left science and became a painter. And I think his paper probably had about, I don't know, order single-digit number of citations until 10 years ago, and now it must have thousands of citations. Okay, and I think Horndeski even has started to write science papers again. But okay, so the small print is the most general scalars, the most general theory of a single scalar field with second-order equations of motion, and that's an important point, because very generically, if you have a higher order equation of motion, you have fatal instabilities. So that goes under the name of Ostrobratsky's theorem. Who did that in the 19th century, not in the context of field theories, if I remember correctly, but for classical mechanics, because also in classical mechanics, if you have a higher order theory, then your theory is unstable. Okay, and so that's why you limit yourselves to second order equations of motion, and what I don't write here is that you can actually then show that there are some ways to look at beyond Horndeski theories, which look like they would have higher order equations of motion, but then there are constraints that eliminate the higher order parts, and so you can have slight like extensions that are still only second order in the equation of motion. So this in some sense is a very general class of theories. There are some subclasses that people like kinetic gravity trading, which is probably there. and Galileans and other things. And then what we will discuss in more detail is that you can use an effective field theory approach, and it turns out that the effective field theory approach gives you effectively the same answer as that. In some sense it has to. Okay. And so that's then roughly what you can do with an additional scalar field by construction, but of course you're not limited to that. You can, for example, have an additional tensor field. So the metric is a tensor field. You can have another tensor field, that's then called bigravity. Or you can try to make a model of massive gravity, and that was actually a big breakthrough in 2010, because it was known how to do that at the linearized level for, by now, I guess, 50 years, work by Fietz and Pauli, but no one could actually do it non-linearly until Deram, Gabadadze, and Tolly, and so that was a big breakthrough. It is, however, not clear how useful this is for the dark energy problem. So the idea a bit of massive gravity is that if the graviton is massive and very light, then you get the Yukawa type potential, and so you cut off you reduce the gravitational force on scales of the inverse mass scale. And so if these are cosmological scales, then in principle your gravity becomes weaker on very large scales, and that might lead to dark energy. And indeed you can show that you get accelerating solutions, but you can also show that you cannot actually get these solutions for a Friedmann, Lemaitre, Robertson, Walker background. So you need to deviate from that background, and there are other problems. So this is interesting work, but it's not at the moment clear how good, whether there is anything that really works for dark energy. Well, it's very complicated. And then you can then you can get a bit desperate, and you can start to put non-linear, non-local operators like 1/over derivatives into your actions and things like that. And then there is even more, because then you can also say, well, okay, maybe we're not actually dealing with 3+1 dimension, we can have extra dimensions, okay? And that was actually very popular 20 years ago or so, or 15 years ago. Also because of string theory, because in string theory you have generically more than 3 spatial dimensions, and then you need to either compactify them, or you need to say, which is kind of generic, that matter fields, they correspond to the endpoints of open strings, and they can be confined to a 3-dimensional brane, while gravitons, they're closed strings, they can propagate into the bulk, which is the part outside of the brane. And so then, because gravity can move away from our 3-dimensional universe, then it can be weakened as well. And but effectively, the extra degrees of freedom, like the size of your extra dimensions, they always look like scalar fields. And so effectively these higher dimensional theories, when you rewrite them in the way so that you have their dynamics in our 3+1 dimensional world, they effectively also look like scalar field theories, and so they're effectively also covered by the models we already looked at. And so, and also it's quite hard to work out these models in a way that they work, and so this became a bit less fashionable. So there are also fashions. So this was very fashionable for a while, now a bit less fashionable. That doesn't say anything about whether it's relevant or not relevant. That's purely some kind of sociological dynamics in the community. Okay, and so there is a lot that can be done. And so I won't go into more detail here, but I will look at slightly more detail at 2 specific examples. Quintessence or K-essence as a prototype for dark energy, and F of R as a prototype for modified gravity, to show you a bit the kind of phenomena that you can find. Okay, and so dark energy. So what is dark energy? And then a few things like tracking, which is an interesting aspect. How do actually the Boltzmann codes, the codes that calculate predictions for observables, how do they implement it? and what are the problems of dark energy. Okay, and so as you probably now see, there is no unique model, but normally dark energy, we also think a bit that it's something relatively smooth, so something that mostly affects the background expansion but doesn't do much else. And so typically we think of quintessence, and quintessence is the model you've already seen so many times, same as inflation, the minimally coupled canonic scalar field. Okay. And so I don't really need to show you the details again, but we already discussed. So you see, that's also why I could, without too bad a conscience, spend some time on inflation, because what we discussed there we can directly translate to here. And so as we discussed for inflation, this is the energy density and this is the pressure of the quintessence type dark energy. Okay. And as we said, you can then change rho, and you can change the equation of state as a function of how your field evolves. And so what you can do, for example, so one of the problems of the cosmological constant is that it stays here below, and so your initial conditions look extremely fine-tuned. And if you can change W, then you can change that. You can evolve along with radiation and matter, and then down here you can take over. And so then you can say, well, isn't this extremely fine-tuned? No, I mean, you have to have exactly the right W to move along. Okay. Now it turns out this part is actually okay, because you can rewrite, I took the slides out, but if you want, I can show them. You can rewrite your field equations as a dynamical system, and you can look for stable and unstable fixed points. And you find that there are indeed stable fixed points where your field exactly follows slightly subdominant. So it remains slightly subdominant, but it follows the dominant, the dominant contribution to the energy density. So during radiation domination, your field behaves like radiation. During matter domination, your field behaves like matter. So it does it, and if it's too high, it actually enters a kinetic phase and goes below. If it is too low, it freezes. And so it's very naturally actually ends up with being a small fraction of the energy density in the universe. So that is not obvious if you just look at the equation, but if you calculate solutions, you find that these solutions exist. And so you see that the equation of state of this dark energy field is 1/3 during radiation domination, and then it becomes 0 during matter domination. But of course, that's not exactly what you want, because what you really want is that at some point it then transitions to something close to -1, corresponding to this point here, where it goes off tracking and then starts to dominate. And that unfortunately, there is no natural way to do that. And so effectively what you normally have to do is you have to either put some bump in the potential or have multiple terms that need to be balanced so that you get kicked off the tracking exactly at the right point, because otherwise you just keep on tracking and then you don't have dark energy. Okay. And so it can partially solve the initial condition problem, but it cannot really solve the coincidence problem. That said, I think as I mentioned it later again, K-essence to some degree can, coupling it explicitly to something else like neutrinos that become non-relativistic also can. So there are ways to get around it again. But then they typically do other things, and then you have to be a bit more careful. Okay. And now a point here is that, okay, so here we have, maybe I should actually, should ask, so apart from initial conditions, there is one quantity that we actually get to choose to decide what our quintessence model is. And that's the potential. So we can freely choose a potential. So then the question is, which potential should we actually use? Well, in principle, fundamental physics should predict it. In practice, not, of course. And but then we can actually turn around the argument. We can say, well, the link between rho and P gives us W. And so effectively, for each potential, I can calculate W, and you can show that to do the reverse. For each choice of W of T or W of redshift, you can reconstruct what the potential is that you need to get this W. And so then you can say, well, instead of giving a potential, I just give W. And that then determines some effective potential that I don't know and don't really care about, because I just put in a fluid with a given W, and I know at the background that has to do the same as the corresponding quintessence model. And so then we can basically just look at this instead of look at that. And our quintessence model actually now has to some degree disappeared. And then you think, okay, that's great for supernovae. How about perturbations? And so then you look at the perturbation equations. So these are the equations we already saw, okay? And now you do all of these calculations at the perturbation level, and then you get the delta phi and the delta. And so you calculate the perturbations to the energy momentum tensor in terms of the field variables, and you calculate your equation of motion for the perturbations in your k-essence field, and then you compare this and that, and basically the energy momentum tensor gives you a dictionary. It tells you that where there is a delta rho here, or delta which is delta rho over rho, I have to replace it with this expression of the fields, delta p, I have to replace with this expression of the fields, and so on. So this calculation gives you a dictionary, and then you look at this equation and find that this equation is actually exactly corresponds exactly to the conservation equation. If you choose the properties correctly, because you remember that delta p and sigma determine your material. Now we argued that we can think of like W determines what the material or your fluid that you have, the nature of the fluid at the background level. At the perturbation level, it's delta P and sigma. And since the W fixes the potential for the field, for us, there is no more degree of freedom. And so therefore, if this is really working, now we need to have a precise prediction for what delta P and sigma have to be in this case. And so it turns out sigma has to be 0, and delta P has to be given by a sound speed, and the sound speed is the speed of light. Okay, and so quintessence corresponds to a fluid with a free W, and with a sound speed that is the speed of light, and with vanishing anisotropic stress. And if you impose that, then up to linear perturbation theory, the two are identical. And so you don't actually need to work explicitly with the quintessence model. You can just put in a fluid. Okay, and that's a big simplification. And actually, that's exactly what Clauss and Camp do. Clauss and Camp, the Boltzmann codes that calculate the galaxy distribution and CMB spectra, they don't solve the field equation. They just solve the fluid equation because it's exactly equivalent. And they actually also allow to change the sound speed squared. And then if you go back to the list of models and you calculate predictions for all your models, then you realize that a free sound speed squared corresponds to the k-essence class of models. So actually the fluid that is implemented in Clauss and Camp corresponds to a k-essence type dark energy model at the effective level. Crucial point, because later, probably tomorrow, but maybe still today, we will reverse the argument and play the game the other way around. Okay. So let me say a few words what the quintessence model does. Actually, I should have first put in another slide, the slide that says the only dark energy that doesn't have any perturbation is a cosmological constant. Okay, now we get to that later. And so one more important point is that whenever you work with non-trivial dark energy or modified gravity, you have to look at the perturbation, unless you really only look at supernova data. And because basically nearly all the observable, they also depend on the perturbation. And so how do the perturbations evolve? Well, here a k-essence field, actually a k-essence fluid. And so what you find is you can get some approximate solution. And so what you find is that the horizon, so this is in time for a given fixed wave number that is given here. And so typical scales is the horizon scale, but now because we have a sound speed, there is a sound horizon. And well, if the sound speed is 1, the sound horizon is the horizon. And what happens is that the perturbations can grow outside of the sound horizon, because now actually I should go back to the perturbation equations a long time ago, because outside of the sound horizon, generically gravity makes the perturbations grow. This is the case when okay, maybe I really should go back to the slides. I think maybe we see them again. Okay, outside of the horizons, the perturbations grow. And then when we hit the horizon, the perturbations stop growing because pressure support kicks in and stops the perturbations from growing. So dark matter, you may remember that dark matter has a 0 sound speed, so dark matter grows on all scales. And so because the sound horizon of dark matter is at k infinity, and so for dark matter it just keeps growing, but the perturbations in the dark energy stop growing inside the horizon. And so inside the horizon, the dark energy perturbations are very subdominant to the dark matter perturbations. And outside the horizon, they're actually given by the ratio of 1 plus W divided by 1 minus 3W. And so typically they're also suppressed, no, because dark matter has W equal to 0. So for dark matter, this ratio is 1. But for a dark energy with W close to minus 1, it's suppressed by something like the deviation from minus 1 divided by 4, roughly. Okay, and so that means that it's at most, because that's already a very high W for the constraints, and so that means it's at most about 5%, but typically even less than 5% than the dark matter on large scale. And so then you can also plot it a bit differently. And here is the relative contribution to the gravitational potential. And so you see for this specific choice, which is here minus 0.9, outside the sound horizon you get 4 to 5% extra contribution. Actually, okay, it's 1 plus the. So you get so 1 means you don't get any, you get no contribution from dark energy perturbations. And so you can see that you get about 4 to 5% contribution outside the sound horizon, and then it goes to 0 inside the sound horizon. And then you can look, okay, what happens if you have nonlinearities? Well, matter nonlinearities actually suppress it further, because matter nonlinearities mean that matter has more perturbation, but then when you also have scalar field nonlinearities, then it decays slower. That's kind of a detail at that point. Actually, there are probably much worse things than that happen, but we don't understand them yet, so I cannot really talk about it here. Okay, and so here is the slide that I should have put much earlier. Okay. So really the only thing that doesn't have perturbations is the cosmological constant, and that's easy to see when we look at these equations, because if W is minus 1, so this here is the psi is the term that drives the basically, if you have so the psi potential is the thing that accelerates that transmits your gravity, the gravitational potential. And so if the gravitational potential is perturbed, it perturbs any fluid. And the only case when it does not perturb any fluid is if the prefactor is 0, and the prefactor is only 0 if W is minus 1. Okay, so whenever W is not minus 1, it's impossible to keep your dark matter, dark energy, whatever, from acquiring perturbations due to the perturbations in the universe that are already there. And let's see. Okay, then I should maybe say, okay, so the sound horizon introduces an additional scale, And that's also very typical. Dark matter has the sound horizon at infinity, it doesn't have one. And so dark matter clusters the same on all scales. And so in lambda CDM, clustering is scale independent because lambda has no scale. It doesn't have perturbations. Dark matter has no scale. So everything clusters. All scales cluster in the same way. But when you introduce dark energy that has a sound horizon, then you introduce a new scale, and this scale dependence is a typical sign of something like dark energy physics. Okay. Then some problems. So why are we not happy with quintessence? Okay. I mean, one of the points that was already mentioned, something we always forget about for all of these models, we somehow have to get rid of the cosmological constant. So there are some ideas, but nothing that really works convincingly. So that's why I'm not really going to say much more. But okay, another thing I already said is you cannot really solve the coincidence problems in a quintessence model. What we didn't see was that in order to get acceleration, you need to be in slow roll, like in inflation. And that means that your potential has to be very, very flat. And if your potential is very, very flat, and you look at quantum field theory, you generically have corrections that are much bigger than your potential. So you somehow have to protect your field theory from acquiring corrections to the potential that destroy your flatness, or otherwise it cannot work. You also have to be careful that you don't couple. Typically in particle physics, such a field would not be totally uncoupled like we wrote it here. It would generically be coupled to other matter, and if you do that, then your theory is dead, because we don't observe any such couplings. There aren't really any candidates. Even the Higgs doesn't really work for that. But in spite of all of this is the standard dark energy, and that also tells you how desperate we are. Okay. And a very quick word now about an additional point that is at least interesting. Okay. So when you look at your rho and your phi, and you look at it a bit longer, then you realize that you cannot cross -1. Okay, you can go to -1, but you cannot actually cross, because this thing is always positive. And that's a bit awkward, because when we calculate, because our data tells us that W is very close to -1, so then our plots are always a bit cut off at -1. Okay, and with the fluid, if I just put in an arbitrary fluid with the W, I can of course put W smaller than -1, because I don't actually calculate my field evolution. I just put the W -1 by hand. And so if I look, let's say, at supernova constraints, then I can also get constraints for W smaller than -1. And also if we have some parametrization, normally the parametrization doesn't automatically respect this limit. And so what can we do? Well, we could of course impose these constraints, but your colleagues, they don't do it, and so they have much nicer plots, and that's bad for your career. Okay. And so you could use a model that can cross. So it turns out that with the complete Horndeski model, or specifically with the KGB, the kinetic gravity braiding submodel, you can actually cross. Okay, that's difficult, no one does that. And so what does everybody do? Well, everybody actually cheats. So everybody actually just freezes the perturbation close to -1 in an effective way, and then goes on once we have crossed -1, as if nothing ever happened. That's also a bit crazy. Okay, so well, everybody does that, me included. But so if you see plots that give constraints on W for W smaller than -1, then you just have to be aware of it. Okay. So, because in principle, this is actually a real problem. Good. So that was the last thing I wanted to say about dark energy. And so now let's look a bit at modified gravity, specifically at f of r. And let's try to get an idea to which degree is a typical modified gravity similar and not similar to dark energy. Okay, and so here is, okay, this is an f of r type action here in this specific one because I'm following Pogosian, not Pogosion. It's r plus f of r, that doesn't make any difference. And so if you calculate your equation of motion, you get this equation of motion. And then you can, pretty much always, you can play a trick. You can say, so this is the Einstein equation, so this is the contribution from the other fields. And then you can say, well, the r mu nu minus 1/2 g mu nu r, this is my gr equation. And so I move everything else onto the right-hand side. And I say this is actually the same as gr with this stress energy tensor and an additional fluid like that. And this you can effectively always do. And so in that sense, modified gravity and dark energy, they're effectively the same. Nonetheless, there are things that are more typical for modified gravity and more typical for dark energy. But if you have to decide what is modified gravity, what is dark energy, this is actually a really hard question. It's basically philosophical more than physical. And okay, then you can calculate. Okay, you can, and you also see that actually here. Okay, so if we calculate the equation of motion, then you can actually also see that, especially in the lambda CDM limit, you get the second order equation of motion for df by dr. And actually a while ago I said that if you have an f of r model, we can think of it as a scalar tensor model where f of r plays the role of a scalar field. And you can really see in this equation here, this is exactly a type of, like a second order equation for f of r, so f of r really looks like a scalar field. And it also, by the way, because here there are no more, because we are in the lambda CDM background, so there is no more degree of freedom actually left, because here we also have, like in quintessence, we have 1 degree of freedom, the function f of r, and so if we fix w, we pretty much fix the form of the f of r necessary to recreate this scenario, and so in principle it's only the initial conditions that are then free. And so actually the models, when and if we ever get to constraints on these models, we will actually be looking at exactly that case, and then we can basically use the value today of f of r as the quantity that fixes this model if we impose a lambda CDM background. Okay. Yeah.
When we work on f of r theories, there are some conditions on the f of r and the derivative.
Yeah.
Positive. There is any relation with this kind of description?
Yes, because I mean they also correspond to things like sound speed squared positive and these kind of. So it's also, yeah. So normally they map quite nicely across. Okay. Okay, and here is then, so for the perturbation level, you also actually have basically a standard scalar field equation. So okay, so just repeats to say that f of r can really be seen as a scalar field that is then maybe called scalaron or so. And you also see that if you look at this as a scalar field equation, you can think of this expression as an effective potential, and the second derivative of the effective potential gives you an effective mass for this scalaron field. And if you have a mass, so they have a massive field that mediates a fifth force, and so that means again that basically that you have like a Compton wavelength, and that the behavior will be different for wavelengths larger and smaller than the Compton wavelength. And so again, also in these theories, you will generate a scale dependence. And so here is an example of the scale dependence. In lambda CDM, you have no scale dependence. So the growth as a function of redshift is the same for all scales. But in an f of r model, you introduce a scale dependence. Typically, the effect is rather stronger for what we would call modified gravity model. The other thing that also happens is that depending, and this is very typical of modified gravity model, that depending on the regime, so normally phi is equal to psi, the two gravitational potentials. Now in quintessence they're exactly equal. But for the FFR models, there is a regime where phi is actually very different from psi. And so this difference between phi and psi in these that's a very typical sign of modified gravity models. And you can also see that the effective gravitational constant changes, and that is also typical, and that usually makes a big problem, because if on small scales you have a different gravitational constant than you should have, then your model is dead, okay? Because solar system constraints totally rule it out. And actually many of these models, for a while, they were considered dead, because solar system constraints rule them all out. Okay? And then people realized that actually you can hide these modifications on small scales, and that is called screening. And basically all of these models need screening. So basically modified gravity models, pretty much all of them need screening, otherwise they are not compatible with local measurements. So another typical feature is that you can look at your theory in two different ways. So this is just a transformation. It's the same theory. You just rewrite it. And so in one frame, which is typically called the Jordan frame, you can rewrite your theory in terms of your scalar field that is coupled to R. So this is a modified gravity theory, but your matter then is typically uncoupled. So your matter, you have normal matter, but you have a modified theory of gravity. But you can make a conformal transformation, and you can rewrite it as a theory where your gravity is Einstein-Hilbert. So your action, so your gravity is GR, but now you have a coupling between your field and matter. And so you can play between these 2 points of view. It's the same theory, and you get the same observations, but from one point of view your gravity is strange and your matter is normal, and from the other point of view your gravity is normal and your matter is strange. Okay. But they are balanced, so they effectively look the same. Okay, I don't really have time to go into details, but that's one of the typicals. Okay, and I just want to mention the fact that we should not forget, even in cosmology, we should, especially when we work with modified gravity theories, we should not forget that there are many additional constraints. So effectively, these fifth forces, these long-range forces, they need these models to be screened. Then in some cases you get new particles, and if these new particles should have shown up at the LHC, your model is dead. You can also have varying fundamental constants, so typically your Newton's constant varies, and that typically is also not a good idea, except that there was for a while people thought they'd seen it. Okay, you have solar system constraints. Sometimes you can also modify stars, the structure of stars, and if stars don't work, that's also bad news for your model. So in extra dimensions, sometimes you can hide your modifications on very small scales, but by now tests show that gravity actually works at least down to 0.1 millimeter. So these are all things. So just one word or a few words about screening. So screening is so screening, as I said, is critical for these theories because you need to hide them. And so in the Einstein frame where gravity is normal, but your matter is coupled, so there the problem is that if your matter is coupled to the field, so if your field is dynamical, it acts as a fifth force on your matter, and we don't see that. And so you somehow have to hide, you somehow have to make this coupling disappear. Okay, and so there are three typical ways to do that. And one of them is called chameleon. And in the chameleon mechanism, so your potential gets an additional contribution. If your density is very high, it gets an additional contribution here that leads to a very high effective mass for your field. And then your field freezes. And if your field freezes, well, then you just may have some prefactor, but you can renormalize that prefactor out. And so your fifth force is frozen, and so you don't see it anymore. Okay, that is called chameleon mechanism. Another one is one where this factor here depends also on the density, and so in a high density region you can write down a model so that your coupling vanishes. So basically in a high density region the coupling goes to 0, and so you have no problem. Okay, high density because solar system is effectively high density region. And the third one, which is typically called Einstein or camouflage. So this is the kinetic function, and if you make this function very large, then the scale of your field in some sense goes up, and so then the coupling becomes small relative to the kinetic function. And this effectively also suppresses your coupling. So these are the main classes of mechanisms that you can use to hide your modified gravity field inside the solar system so that you can actually pass constraints. But typically, all of these are non-linear mechanisms. And so to actually see how they work, you need to run numerical simulations, and that's quite hard. I mean, it just costs time and effort. Okay. And so here is just basically what I already said about the chameleon mechanism. So if you have a massive scalar, then you have a Yukawa type behavior where the forces decay with this exponential here. And so if you want to hide the fact that you have a scalar, so typically the mass scale here is very low. It's basically inverse Hubble scale, because you want your scalar to act over very long ranges. No, otherwise it cannot affect the universe. And that means that your field is active over very long ranges. And so then the goal is to locally and only locally crank up the mass in order to shield the field. Okay. And so then typically you do this by looking at the effective mass that is in the potential, but an additional contribution due to the coupling to the matter. So here the coupling itself helps you to hide the field. Well, the coupling is the problem, but here it's also the solution. And so then you get from a low mass, you can get to a much higher mass. So here is an example from some n-body simulations. And so you can see that in some limits, if you turn on the chameleon mechanism, suddenly the field gradients totally disappear. And in that case, you have no effect anymore. While if you didn't have the chameleon mechanism, they would still be there and they would be causing problems. This was very fast. But it's more to tell you that this exists. Okay, so now I have a few more minutes. Is there any questions up to here? Okay, this was a very fast run through the basic models and their main consequences. I see everybody looks at me with a bit shell-shocked. Yeah.
Is Jordan and Einstein trend completely equivalent even in the presence of matter radiation dark energy?
Yeah, in my opinion, yes. Yeah, because you use that, right? In one case you're coupled to that, in the other case not. I think there is always some debate, but I don't see how they can differ. Actually, aren't we writing a paper about? We discussed about that also with Luca. Yeah. Okay. So let me start a bit with the unified modeling. And so what are the motivations? So yeah, well, you saw that I was very quickly running through these models. And I only mentioned a few. And already there are too many, okay? And so are we really sure we have all the models? And we have to do all of this work for all of the models, okay? And so the alternative is to use some kind of supermodel that contains many of these models, okay? And so there are two ways to do it. We already a little bit talked about that without probably you realizing, so that's where we work with the effectively fluid models or similar, but we can also try to write down a unified model on the action side. And well, in some sense, Horndeski tried to do that, but there are ways to do that with a more principled approach. And they're called effective field theories. And I think I just have the time to explain to you when do we have to stop?
You have 7 minutes.
Okay, so let me explain to you the effective field theory of elasticity in 7 minutes. Okay, so now I can slow it down. Okay, because when I did that slide, I was teaching elasticity. But okay, so how do you? Here is a pointer. Okay, you would like to characterize its properties under deformations. So how do you do that? So you could try to model its internal state with a huge number of molecules that are all linked, and then when I push here and here, you could calculate ab initio how the forces go through. That's very hard. Okay, so you don't do that because you are really only interested at the behavior in the limit when this is effectively a continuous body. Okay, let's say we want to model this as a continuous body. How do we do that, and how much information do we need? So first we need to decide what is our degree of freedom that we want to model, and here it is the deformation, which is given by the deformation tensor, which is if you deform your body, well, you get a vector that tells you the difference between before and after deformation. This is this u vector, but it is not actually this u vector that is relevant, because if I take this and I move it, I generate a u vector, but I don't generate the deformation. So it's the variation of the u vector that is relevant, okay? The fact that my u vector here is different from here. And so that's why it's the derivative of u. Okay, this is called the deformation tensor, and this is the object that we are interested in. And then we have to somehow get a typical quantity, like the energy, for example, and we just do a Taylor expansion of the energy in terms of the u vector to some low order. Okay, so we have some constant contribution, we have the first derivative times uij, we have the second derivative times uij ukl, and then we would have the third derivative and so on. Small, no, we look at small deformations. Now in this case, the first order actually disappears because of what it means, right? Because these derivatives, this Taylor expansion is, you want to evaluate it around the undeformed state, and so in the undeformed state, this term vanishes, and so what you have to characterize your deformation, you need to give all of these constants. Actually, all of these functions, okay. And that looks quite scary. So, but now you want to simplify the problem, and so you say, well, I would like a model that obeys certain symmetries. Specifically, I would like homogeneity. I assume that this stick is homogeneous, which it isn't, but okay. And that means these quantities here, they cannot be functions of x, they have to be constant. And in addition, I want isotropy, and isotropy means that the lambda here cannot actually depend on the direction, and so I have to find, so these can only be scalar quantities, and so I can ask, how many scalars can I create from two tensors? Turns out you can get two scalars. You can get the trace squared, or you can get the full contraction. And so this huge number of functions now, it has just turned into two scalars, lambda and mu. And so you can fully characterize the response of a body under a deformation with two numbers. That's quite surprising. But the point about these two numbers now is that you don't know what they are. So the idea is that you have to go and measure them. That's the kind of the fundamental points about the effective field theories. you don't want to calculate them, you go and do 2 deformations to measure the 2 numbers, and then you can predict all the other deformations. And that is what you do in elasticity. And okay, some other points are that's only valid in a certain regime. So if you have a strong deformation, it will break. You cannot describe that. So it's the low energy regime. Also because you impose isotropy, well, for a crystal you need different conditions. And you can write it in different ways. You can write it like this, or you can write it in terms of bulk modulus and the shear modulus for those two. But it's actually okay. So now in my last 2 minutes, let me just read. Let me do the same now for GR. So if you want to do dark energy, well, we need to identify degrees of freedom, and since we work in GR, we will work with geometry, and specifically we will split space-time into space and time, and we want to look at deformations of space. Okay, and so the geometry can then be written down as well, actually space and time, as the Ricci tensor on the spatial Ricci tensor, the extrinsic curvature, and the G00 for the time direction. And so you write a Taylor expansion in these quantities. Okay, so you have the extrinsic curvature, the derivative, the R, the derivative, G00, which is also called N, and the derivative, and you go to second order, and it's exactly the same as before, except that now you have the geometric quantity. And then you have to impose isotropy and homogeneity, and you have to impose constraints that you don't want more than second order equations of motion. And that's also exactly the same as before for elasticity, except it's a bit less obvious. And then what you get is this action. And this action, that's just EFT. This is the EFT action. But you do really, it's the same procedure in both cases. You look at how to describe your effective degrees of freedom. So you choose geometry in both cases. Actually, you do an expansion, and you determine, okay, given your symmetries, which constants actually describe your thing. Okay, here they become functions of time because we are isotropic, we are homogeneous in space, but we have a time evolution. So in the EFT of dark energy, the constants are actually functions of time. But you can see, right, you can only have full contractions or trace squared, and so that's actually exactly the same as before. So you literally have the same terms. And then you can rewrite it in different ways, also exactly as before. And I should be stopping here.